Hello and welcome. My name is John Horvath. This presentation is about residual loads from deep foundation installation. They are the elephant in the room that deep foundation industry stakeholders need to address. Let me begin with some comments as to why I've made this presentation. This presentation focuses on deep foundation elements, and I'll refer to them as DFEs, that are subjected to externally applied axial loads after installation. Although, as we will see, there are important outcomes that are relevant to DFEs that are subjected to post-installation horizontal and/or moment loads as well. Although the concepts presented are applicable to all types of DFEs, regardless of their manufacture and how they're installed in the ground, my focus will be on driven piles, as the vast majority of research and relevant data were obtained for this type of DFE. Now, it has long been recognized that the traditional assumptions that a DFE is initially stress-free after installation in the ground, and under subsequent axial loading, which is usually applied at the head of the DFE, the ground is only a passive, reactive-only participant that only provides geotechnical resistance for a DFE. Well, these two common assumptions are simply incorrect, and I'll explain why as we go through this presentation. So in reality, there are several distinct physical mechanisms that generate axial loads on a DFE that can develop within the ground, both during and after DFE installation. And these mechanisms are independent of the traditional shaft and toe resistance mechanisms that we associate with post-installation externally applied loads. Now, although these ground-induced physical mechanisms interact directly with the DFE shaft, as we'll see, they indirectly produce effects at the toe of the DFE as well. So the thesis of this presentation is that it is mission critical that all stakeholders in the deep foundation industry, and that includes design professionals, academicians, project owners, construction contractors, material suppliers, the testing laboratories that are responsible for construction quality control and assurance, as well as industry organizations such as the Deep Foundation Institute, DFI, that bind them all together. So all these stakeholders need to recognize and deal with these ground-induced physical mechanisms on a routine, everyday basis in both design practice and academic instruction and research. And this is something that is either not done or not done correctly at present, even though the existence of these physical mechanisms within the ground has been known and documented in the published literature for decades. And I think this quote that I took from a book written by Aldous Huxley really sums things up very nicely. There are just certain facts that are always going to be there whether we choose to consider them or not. Now, before moving on, I do want to digress a bit and make it very clear that I have received no compensation from any organization or individual to make this presentation, nor have I received such compensation for the last several decades when I have been very actively involved in deep foundations related research. The reason I'm making this presentation is that I literally have been involved with deep foundations since the very first week of my professional career, which goes back more than 50 years now, to June of 1972. I've been involved with deep foundations both as a design professional, as a licensed professional engineer, as well as an academician involved in academic instruction and academic research. Furthermore, I am a charter member of the Deep Foundations Institute, DFI, which was founded in 1976 and was involved in helping to write some of their early publications. So the point is, I've been very intimately involved with deep foundations for my entire professional career of over 50 years. And I've simply come to see that residual loads and other things I will talk about in this presentation are very, very important in the performance of deep foundation elements. So let's move on next to some background as to what I am going to be talking about. Now, the existence of ground-induced physical mechanisms that generate loads in DFEs was suspected for driven piles, at least as far back as the 1950s. There are technical papers where the authors comment that they suspect that there's something residual within the piles after they're driven, although they weren't able to quantify it. These were just qualitative comments. However, the existence of these mechanisms was proven conclusively by research performed in the late 1960s that was published in the early 1970s. Now, more recent research has demonstrated that these ground-induced physical mechanisms can develop with any type of DFE. So clearly they're an industry-wide issue. They're not just a driven pile issue. So because these ground-induced physical mechanisms can develop even in the absence of post-installation externally applied loads, and this is a very important thing to appreciate, there are countless case histories where a deep foundation element has failed, if you will, geotechnically, and failure in this case defined by settlement of the DFE tens of millimeters, several inches, or even meters or feet in extreme cases, even though there was no externally applied load on the DFE. And really, this is very clear when you look at any number of case histories where a DFE has literally been pulled downward out of a pile cap. And this is one example that I found online. Here we have a structural slab supported by pile caps, supported by presumably driven piles. And we see here that one of these piles has pulled away from the pile cap. So the ground is literally pulling this pile down, in this case, quite a few inches, it would appear, as the result of the ground having settled, I would say, probably a couple meters, several feet. This is very similar to, I began my career in 1972 working for the Port Authority of New York and New Jersey, here in the New York City metropolitan area. And one of the things I learned about very early in my career was some of the original aircraft hangars at LaGuardia Airport in the borough of Queens in New York City. LaGuardia Airport was built in the late 1930s on land that was reclaimed from a marine tidal area. There's over 30 meters, over 100 feet of normally consolidated organic clay under the site, and the entire airport site has undergone several feet and meters of settlement in its lifetime. And some of the original hangars, which were all pile supported, have experienced this type of extreme ground subsidence, literally pulling piles out of a pile cap. So my point is, this is not just a one-off. This is a situation that has been seen many times around the world. Now, although ground-induced physical mechanisms act independently, the physical mechanisms associated with DFE resistance to post-installation externally applied loads, there is additive force displacement interaction between these two categories of physical mechanisms because both have identical geostructural cause-effect behaviors. And this is quite important because this additive interaction should always be considered explicitly in both design practice and academic research because the net effect of the combined physical mechanisms produces vertical loads on and vertical displacement in the form of settlement of a DFE that impact DFE performance both geotechnically and structurally. And I will, of course, illustrate these as we get into this presentation. And of course, this settlement can in turn impact the performance of a structure that is supported by DFEs. Unfortunately, despite the fact that these ground-induced physical mechanisms have been well documented in the published literature for over 50 years now, because these mechanisms develop out of sight, if you will, they are all too often out of mind in both design practice and academic research. And by the way, the reason I keep focusing on academic research, of course, is that academic research is where we get the analytical methods that we use in design practice. So we need to discuss both of these aspects together. Furthermore, even when these ground-induced physical mechanisms are considered, all too often they're dealt with incorrectly. And that's because our understanding of these mechanisms has really gone through a lot of change over the last 50 plus years that we have known about them. Unfortunately, it's extremely problematic that incorrect methods for dealing with these ground-induced physical mechanisms exist, because experience has shown up to the present that they are sometimes incorporated into building and design codes that have legally require compliance and thus mandate their use in practice. The point being is that if you have some sort of code that a design professional must follow on a project, they're going to be forced into using an incorrect method. So, having identified the existence of ground-induced physical mechanisms affecting DFEs of all types, and the mission-critical need to consider these mechanisms in both design practice as well as academic instruction and research, the next step is to identify and discuss the specific details of these mechanisms. As we'll see, there are two independent sources of these ground-induced physical mechanisms, and they both have the same root cause, load source, and concomitant overall effect on a DFE. So we can discuss some of the common elements before moving on to the specifics. Now, this graphic illustrates the terminology and notation I'm going to be using in this presentation. This specific graphic comes from a 2020 monograph on tapered piles that I researched and wrote, and it's based on information that I found in several publications by Dr. Bengt Felinius. Now, the root cause of all ground-induced loads is a downward acting shear stress or negative shaft friction that acts along a DFE shaft, and in this case it's called the unit drag load because literally it is dragging down on the shaft of the DFE. Now, whether the causal mechanism of unit drag load is downward displacement of the ground relative to the DFE, or upward displacement of the DFE relative to the ground, or some combination, it doesn't matter for the purposes of this discussion because the net result is the same, and that's the important thing. So regardless of the specific causal mechanism that produces the unit drag load, this unit drag load, shear stress integrated over the surface area, external surface area of the shaft, produces an axial compressive force called the drag load within the DFE shaft. Now, I noted earlier that unit drag load can develop from two distinctly different causal mechanisms that in any given project can develop independently of one another. So you can have either or both. You can have residual loads that develop as the result of DFE installation, and you can have global settlement around and perhaps even below a DFE as well that develops over time after the installation of a DFE. And these global settlement can be the result of any number of different natural and anthropogenic causes. Now in this presentation, I'm only dealing with residual loads. I have another presentation that's in the works where I talk about global settlement as well, but I'm only going to be focusing on residual loads. And that's because they develop even in cases where global settlement does not. Global settlement is very, very site and project specific, whereas residual loads are much more universal. They're found for all types of DFEs anywhere in the world. Now note, I don't want to minimize the potential importance of global settlement, as experience has shown that it can be the more significant load and displacement source at a specific site and DFE application, as I showed you a few slides ago in the case of a pile that was literally pulled out of the pile cap. Certainly ground settlement was the predominant mechanism of concern there. So although this this presentation focuses on residual loads and global settlement do have much in common in terms of their cause effect on a DFE. So there are two aspects of a general nature that I want to discuss before I focus exclusively on residual loads. Now the first behavioral aspect that both residual loads and global settlement have in common is that we use the concept of an equilibrium plane. Now, when you look at the published literature, what I will be calling the equilibrium plane was called the neutral plane in published literature up until very, very recently. Even this change has only occurred within the last year or two. For decades before that, Fellinius and others were using the term neutral plane. So these mean the same thing. I think equilibrium plane is actually a little bit better term because it really focuses on what is going on, as I will get to in a bit. So what happens at the equilibrium plane? They change from unit drag load, right, downward or negative shaft friction, to unit shaft resistance, which is positive or upward shaft friction, occurs at the equilibrium plane. And if you have a problem with global settlement, the vertical displacements, settlement of the DFE and the ground are exactly the same at the equilibrium plane. In cases of global settlement, above the equilibrium plane, the ground settles more, sometimes much more than the DFE. They both settle the same here, and then the ground actually settles less than the DFE below the equilibrium plane. One of the things to appreciate is that the equilibrium plane is a dynamic feature in any problem. It will vary up and down as a function of both post-installation, externally applied load, as well as time. So this is not fixed in space and time for a given problem. And you'll see this in some of the case histories that I will talk about later on in this presentation. Now, the second behavioral aspect I want to discuss, perhaps even more important than the first, is that regardless of the causal mechanism, the unit drag load and the drag load that it imparts within a DFE shaft never, and I can't emphasize never too much, reduce the geotechnical ultimate limit state, ULS, or failure load, if you will, of a DFE, and thus never reduce the ultimate load or capacity, if you want to call it colloquially, that can be applied to the head of a DFE in axial compression. The simple reason is because the geotechnical ULS, whether it's soil on soil or soil on solid, as in the case of a DFE shaft, is always reversible simply by reversing the direction of relative displacement along a failure surface. And that's one of the unique things of the behavior of a particulate material like soil, is that you can reverse the failure direction and it's no harm, no foul. You can go fail it in the other direction. Even after it's failed in one direction, you could unfail it, if you will, and then go fail it in the other direction. And you could go back and forth like this indefinitely. In fact, if you think about it, that's what occurs when you drive a pile in the ground. You fail it continuously as it goes into the ground. And the reason I'm emphasizing this is this single fact is where the understanding of residual loads especially has come into play over the last 50 years. When we first began to understand residual loads and global settlement as well, there was a certain perspective that they kind of permanently took away from the soil strength. We now realize that that's an incorrect understanding of the problem. They don't take away from the soil strength. Right? Residual loads and global settlement do not reduce the soil strength, period, of a DFE. And that's probably the single biggest change that has occurred with our understanding of residual loads and global settlement over the last 50 plus years that we've known about them. And again, I'm emphasizing this because it turns out this is where building and design codes tend to make a mistake. They tend to be locked into the old 1970s understanding of residual and global settlement loads, and they really haven't, for whatever reason, they haven't come around to the current understanding of the situation. And again, I will illustrate this quantitatively with case histories later in this presentation. So the bottom line is that unit drag load, of course, can be turned into unit shaft resistance simply by reversing the direction of displacement of a DFE relative to the surrounding ground. Again, just because the soil pile or soil DFE interface has failed in one direction, simply by reversing the movement of the DFE, we can unfail it, if you will, and then go fail it going in the other direction. And in most cases, this only requires several millimeters or a fraction of an inch of displacement to accomplish this. So we're talking about fairly small displacements to cause this unfailing and failing in the other direction. So as a result of this, if a DFE that is subjected to drag load, negative shaft friction, were to subsequently settle relative to the surrounding ground, for example, you apply an external load to the head of the DFE, that drag load would eventually turn into resistance or positive shaft friction. And I will show you quantitatively some numbers that were measured in some really seminal load tests that were done in Norway as far back as the late 1960s. So it's very clear, the bottom line is very clear that regardless of what causes drag load, residual loads, global settlement, whatever, that dealing with it is always a settlement issue. That is, it involves the geotechnical serviceability limit state, SLS. It is not a soil strength issue, the geotechnical ULS. And again, I'm emphasizing this point because this is where building and design codes tend to be incorrect, is they don't appreciate this fact. Now, of course, as I'll discuss later in this presentation, we always have to consider the structural strength, the ultimate limit state structurally of a DFE shaft. And that's because drag load imparts an additional axial compressive force and concomitant material normal stresses within a DFE shaft. So to formally state what I was saying on the previous slide, this issue of how to properly understand and treat drag loads in design practice, regardless of their source, that is, whether residual loads or global settlement, is emphasized here, as experience has shown that this issue has been and continues to be incorrectly dealt with in many building and design codes and other design-related documents that have significant legal and technical control over design practice. And this is not just my opinion. This point has been made repeatedly by Dr. Bengt Felinius in numerous publications over the span of decades, not years, decades. Yet this issue continues to be dealt with incorrectly. For whatever reason, those responsible for producing codes, design manuals, and such appear to be tone deaf to the current understanding of this issue and remain locked into old, now deprecated views of how to deal with drag load that date back to the 1960s. And again, I can say this from firsthand experience. When I started my professional career in 1972, the way that drag loads were dealt with is very, very different than our current understanding of how we should deal with them. Unfortunately, all too many design documents are still based on decades old, now deprecated views of how to deal with drag loads. Well, as I said earlier at the beginning of this presentation, ignored facts do not disappear. I'm adding my voice to that of Felinius, making this presentation in the hope of raising awareness and instituting change. So the bottom line is this is why I decided to make this presentation. I've come to appreciate, based on my research for over 20 years now at Kennedy Airport in New York City, that residual loads are a very, very important consideration. And because they're not dealt with correctly, I really felt motivated to make this presentation to, if I can convince a few people to change their minds on how they do things, it certainly will have been worth the time. Well, now let's get into the heart, if you will, of this presentation, the detailed discussion of residual loads from DFE installation. I will not be talking about global settlement further in this presentation. So residual loads, again, refers to the system of negative and positive shaft friction plus toe bearing stress that exists after DFE installation and prior to the application of externally applied axial load. So there's no external load on the head of this DFE, but within the ground we have both downward acting and vertical acting shear stress along the pile shaft, and we'll actually mobilize at least some of the toe end bearing stress as well. So again, although unit drag load and drag loads only act along the shaft, they will result in load below the DFE toe as well. Now, in the traditional, what I call wished in place model of DFEs that you see in textbooks and other documents, of course, these stresses in the equilibrium frame simply don't exist. And the DFE is assumed to be stress-free after installation. And I do want to point out that although I'm talking about the geotechnical aspects here, we'll see that this wished-in-place stress-free assumption has some very, very significant ramifications for the structural design of at least certain DFEs as well. So this stress-free assumption applies to both the geotechnical and structural aspects of DFE design. Now, residual loads are conceptually identical to the residual, or sometimes they're called rolling stresses or mill stresses, to the residual stresses that you find in hot rolled. I'm adding cold form to here as well, because cold form sections have been and are used in some cases as deep foundation elements. For example, the well-known monotube pile in the United States or North America in general was cold formed. And you also get residual stresses in fabricated steel sections. So here's the typical residual stress distribution in a hot rolled H section, such as an H pile. And if you were to weld together a box section, you would get residual stresses as well. And this welded thing, or this welded situation, is important because, as we'll see, the way that we make the steel pipe for pipe piles, or some call them tubular piles these days, involves welding. Now, the residual loads that act on a DFE produce a depth-wise variable net compressive force and concomitant compressive stresses within the structural materials that comprise the DFE shaft. And again, we make use of the equilibrium plane concept to define the unique point in vertical space where the vertical resultant forces, the drag load, resistance, shaft resistance, and toe resistance produced by residual loads are in vertical force equilibrium. So again, in a nutshell, this is residual loads. You have forces between the DFE and the ground after insulation, even though no load has been applied to the head of the DFE. And again, although we're focusing on axial loads, I will show you that in certain situations, if you had horizontal or moment loading applied to the head of a DFE, these residual loads can be important as well. Now, the axial compressive force within the DFE generated by this combination of forces reaches its peak at the equilibrium plane. Note, however, that the axial compressive normal stress within a DFE shaft may or may not peak at the equilibrium plane. This depends on whether or not the cross-sectional area of the DFE varies with depth. So you have to be very careful. I've seen people make the mistake of always assuming that the stress in the DFE shaft peaks here as well. It may not. It depends on the geometry of the DFE. And again, I will show you with case histories later on what I'm talking about here. So you have to always be careful and when you're looking to check where the maximum normal stress within the DFE shaft occurs, compressive normal stress, it may or may not occur at the equilibrium plane. You have to check that on a case-by-case basis. Now, the reason I call residual loads the proverbial elephant in the room of deep foundations is that few industry stakeholders at present, or past for that matter, seem to want to recognize them, no less address them in a thorough, comprehensive manner in both design practice and academia. And by the way, I emphasizing academia. Not only have I spent more than 30 years of my professional career working either full-time or part-time in academia, as I noted before and will note again, academia is where we get a lot of the design methodologies that we use in practice. So residual loads are the elephant in the room, despite the fact that the existence of residual loads, at least for driven piles, was suggested in publications since at least the 1950s. And their existence for driven piles was proven in the late 1960s by some very seminal research performed at the former Norwegian Geotechnical Institute sand site on Holmen Island in Drammen, Norway. And I'm going to talk about the NGI tests a little bit later in this presentation. I say former sand site. The site simply became overdeveloped, and NGI has since opened up a new test site where they perform things related to sand subgrade conditions. Now, there was a flurry of international research interest and concomitant publication in the 1980s with the overall goal of being able to forecast residual loads for driven piles at least, so that a design professional can use it in his or her work. And you can, these are just several papers that I found, and you can see that there were the people involved as authors or co-authors at the time were big names in the business. The late Professor George Goebel, Dr. Poulos, and Dr. Lovell. These were some of the big names in deep foundations. Dr. Poulos still is. Now, for whatever reason, unfortunately, this research appears to have gone nowhere and has since been forgotten by most, although, as I said, Fellenius has continued to research and write about residual loads with regularity up to the present. As an aside, it's of interest to note that the recognition of drag loads due to global settlement also originated in the 1960s. I remember that the very famous geotechnical group at MIT, Massachusetts Institute of Technology, here in the United States, did some very early research involving drag loads due to global settlement. In this case, the research has continued to the present, which I find a bit surprising. I mean, global settlement, yes, it's a potential significant DFE issue, but only in very specific geological settings, typically areas where we have relatively thick deposits of fine-grained soil that are either normally consolidated or very lightly over-consolidated. So that's why a lot of this research has either been done in Norway or other places where these geologic settings exist. But my point is that global settlement, while important, is very geographically regionalized, whereas residual loads are a potential DFE issue everywhere throughout the world for just about every type of DFE. Largely due to Fellenius's efforts in recent decades, we now recognize that residual loads can develop in many types of DFEs, in addition to driven piles. Although clearly the relative magnitude of residual loads varies widely depending on the specific type of DFE, and most importantly, how it's installed in the ground or created within the ground. Note that some fundamental research still needs to be done for some of the newer types of DFEs, some of which are proprietary, that are either drilled or torqued into the ground. And for whatever reason, those who are promoting these newer technologies either have not undertaken the necessary research about residual loads, or if they have, they're not publicizing what they've learned. What is known at present is that residual loads are especially significant with driven piles and jack piles. Jack piles are really not common here in the United States, as best as I can tell, but I do see them used in at least in Asia to some extent. And for driven piles, at least, residual loads are most significant with tapered piles, such as the monotube and taper tube. And again, I'm going to be illustrating these things later with some case histories. I think part of the reason that residual loads are so significant with driven piles is because of what I call the 2 steps forward, 1 step backward nature of conventional pile driving. This simple animated GIF just illustrates basically what happens when you drive a pile into the ground using conventional impact driving. Although there is net movement of the pile into the ground, it's not monotonic. It goes down and then rebounds with each strike of the hammer. And this next slide illustrates this quantitatively. This is based on some research that I quote here. So what we're looking at is the displacement of a pile into the ground, and on the horizontal axis we're looking at time. So the time between each of these spikes is 1 blow of the hammer, in this case a little bit more than 3 seconds apart. I'm going to invert this graphic so it's more intuitive. So here we come along and the hammer strikes the pile, it goes into the ground, and then the pile actually moves upward, oscillates around, and then settles down to a steady state value before the next impact. So this would be what we would call the final set, usually indicated with the letter S, that we would record for this hammer blow. So if we were to say, okay, from this hammer blow, the pile went into the ground so much of an inch or so many millimeters or whatever, this is just the net penetration or movement, downward displacement into the ground. There was actually much greater displacement, and then it has rebounded back up. So I think we could see intuitively why these residual loads would be so significant with driven piles, because the pile actually moves up relative to the ground in the latter part of a given hammer blow. And as I said earlier in this presentation, when it comes to unit drag load, it doesn't matter whether the ground goes down relative to the DFE or the DFE goes up relative to the ground, or there's some combination of the two. The net outcome is the same. You get drag load. Now, as I said earlier, despite the overwhelming, ever-increasing body of knowledge as to the existence of residual loads for pretty much all types of DFEs, the current design state of practice, and this is true for most academic research as well, is to simply ignore these loads and continue to use the traditional wished-in-place stress-free model for installed DFEs that we now recognize is always incorrect to varying extents. So not dealing with residual loads, as best as I could tell, is the net result of at least 4 different reasons. One is true ignorance of the subject. And I say this from a first-hand basis. Certainly early in my career, I was ignorant about residual loads. All the professors I had in all of my undergraduate and graduate education, none of them ever spoke about residual loads. There's simple dismissiveness of the subject. People think it's just some academic curiosity, and why waste my time? I'm a design engineer. There's the belief that such loads are insignificant in routine practice, so can safely be ignored, and the belief that such loads and their effects disappear when we apply external load to DFE after installation. Now, reasons 1 and 2 are simply ignorance is bliss, and I'm not going to me, that's not a defensible position, and I'm really not going to discuss this further. Perhaps one of you who's listening to this presentation was ignorant of residual loads. Well, now you're not. So I consider that certainly a positive from this presentation. The point I'm getting at, I really can't argue that I can't defend ignorance is bliss. That's why I'm not going to discuss it further. However, reasons 3 and 4 are legitimate, or they turn out to be incorrect, but they're legitimate issues to raise and to address in some detail as to why they are incorrect. Now, I'm going to discuss reasons 3 and 4 together, as they have many overlapping elements in common to illustrate why they are incorrect. Now, in the discussion that follows for the rest of this presentation, I'm going to discuss the effect of residual loads on both the geotechnical and structural behavior of DFEs, as both aspects are mission critical for DFE performance after installation. But as we'll see, there are some important differences between the geotechnical and structural aspects. I'm going to be using case history examples for 2 sites for which I found sufficient data in the published literature. One is the NGI Holman Island site. There was a very nice paper in the 1973 International Geotechnical Engineering Conference. And I'm also going to be talking about my experiences at Kennedy Airport, the John F. Kennedy International Airport here in New York City. I've done extensive research at this site over the last 25, 30 years. It's literally where I started my professional career in June of 1972, the very first week I started working after I got my master's degree. In recent years, I've published 4 white papers about JFK. If you're interested, you can find them on ResearchGate. You can download them as PDF files. And I have 2 narrated PowerPoint presentations that you could find on my YouTube channel. So first I want to talk about issues that affect the geotechnical behavior of a DFE. As you'll see, while residual loads have an overall positive effect on the geotechnical behavior of DFEs that are subjected to axial load, there can be some very significant negative consequences if you don't account for the residual loads properly. This is because not considering residual loads produces data interpretation errors that tend to be on the unconservative and therefore potentially unsafe side, in that they produce a DFE that has an actual geotechnical safety margin that is less than what is either intended or believed based on data interpretation that neglects residual loads. Well, I first want to discuss the Holmen Island, Norway test piles. This was a 1969 test pile program. They installed a total of 4 piles. I'm going to be discussing one of them. All of the piles were precast, pre-stressed reinforced concrete, nominally circular in cross-section. What made this such a wonderful test program and the data so useful is that the load measurement devices were installed in the piles as they were being manufactured. So they were able to make measurements at all stages. Furthermore, they extracted all the piles. So they were able to extract the piles and re-zero all the load measurement devices. So they had a system of checks and balances by being able, that allowed them to have a high degree of confidence on the data that they recorded. Now, the pile I'm going to be focusing on primarily in this presentation, this was one of the longer ones. It was 16 meters, so a little bit more than 50 feet installed into the ground. And it was generic in that it had a constant diameter from head to toe. So it's about as typical of a driven pile as you could find. Now we know that the horizontal effect of stress acting, the ground acting on a DFE shaft, can be expressed as a dimensionless earth pressure coefficient, capital K sub H, times the vertical effective stress, overburden stress along the shaft. And nowadays, the preferred way of expressing this is as the ratio of KH to KO times the vertical effective overburden stress. Now, in this case, K sub O is the coefficient of lateral earth pressure at rest prior to installation of a DFE. So by expressing it this way, and I do want to credit the late Professor Kolhowie at Cornell University in upstate New York with educating me about this KH-KO ratio. That's where I first saw this method used, and I've really become quite a believer in it. It's really a wonderful way of understanding what is going on with deep foundations. Because clearly, the K sub H, what this is saying is that the K sub H really builds on what is already there in terms of K sub O prior to installation of the DFE. Now, for a driven pile, you would expect this ratio to be greater than 1. In fact, for a tapered pile, it's considerably greater than 1. But perhaps for a drilled shaft, what is called a bored pile in many parts of the world, you might have a KH over KO that was 1 or even less than 1. due to the stress relief that occurs when you excavate a hole in the ground to create the drilled shaft. Now, at this particular site, the K sub O, I estimated based on a seismic piezocone sounding. I was very fortunate that the raw data for a seismic piezocone sounding were provided to me. I have to thank Dr. Paul Main, who's recently retired from Georgia Tech in the United States, for providing me with this seismic piezocone sounding and allowed me to make an independent estimate of KO. So this is where the KO came from, and I highly recommend the use of the either a seismic piezocone or just a piezocone to make this sort of data interpretation. So both KH and even more so KH-KO ratio are useful metrics for both drag load and resistance, and that's what we see here. So anything on this side with a negative number is a drag load, and this is a resistance. So if we look at the residual loads, this is the dashed green curve, we see there is considerable residual load from installation. And again, this was an all sand site, so we would not expect much, if any, global settlement. So all of these drag loads are from residual loads from installation. So quite a bit of drag load. In fact, the equilibrium plane after installation is a little bit more than halfway down the pile shaft. All right. And again, you could see whether you look at KH or the KH-KO ratio, you could see the drag loads, the negative values here, and then the transition at the equilibrium plane to resistance. Now, in this case, about 50% of the ultimate toe resistance was mobilized as a residual load. It doesn't show up on these plots, but I'm just adding this to give you some perspective. And this is a not uncommon type of value I've seen. You could get quite a bit of the ultimate toe resistance mobilized as drag load with driven piles in coarse grained soil. So now so clearly what this means, because we had about half the toe resistance already mobilized just by installation, post-installation externally applied axial load at the head of the pile was accommodated primarily by shaft friction, and this included reversing drag load into resistance along the upper portion of the pile, adding to the resistance on the lower portion, and of course adding to the toe resistance eventually as well. Now the pile was loaded in compression rather significantly to about 65 millimeters pile head settlement, so a little bit more than 2.5 inches. And this corresponded roughly to a value that NGI called Q90. So Q90 was a parameter that NGI used at least circa 1970 to define the ultimate geotechnical resistance of a driven pile. So the bottom line is that enough load was applied and the pile settled sufficiently to basically load it to what we would consider to legitimately be a geotechnical failure. I'm highlighting the half of Q90 load level because this might be an assumed service load level, right? If you measured Q90, the ultimate geotechnical resistance, in a pile load test such as this, it would not be unreasonable to apply a safety factor of 2 and say that this was quote unquote the allowable load on the pile. So for discussion purposes, half of Q90 represents the maximum service load level, allowable load if you will. And you see that of course we have had the drag loads are reduced, and down here the drag load is converted to resistance And not surprisingly, the equilibrium plane goes up. So several things to note here. As I said earlier, the equilibrium plane in a given application is a dynamic feature. And in this case, it goes up under the application of external load. And we see here very nicely with the drag load converting to resistance, that very unique nature of soil, that you could basically take a soil that has quote unquote failed, reverse direction of movement along the failure plane, unfail it, bring it to a neutral position, and then fail it in the other direction. And that's what's happening here. All right? The soil went to a neutral, unfailed it to a neutral position, and then brought it to a movement in the other direction. But we note that even under the service load level, there is a not insignificant amount of drag load still acting on the shaft. And this is very important. What this illustrates is drag loads don't magically disappear when you apply a service load to a deep foundation element. They're out of sight and therefore they're out of mind, but they are still there. And this is another very important thing to appreciate from this graphic, that drag loads residual loads from installation do not magically disappear when we start to apply external load to a DFE. Now in this case, the pile had to be loaded to this ultimate limit state in order to overcome all the effects of residual load. So by the end of the load test, all of the drag load had been converted to resistance, although the resistance is still fairly low in this upper part of the pile. And in the process, the equilibrium plane is now at the ground surface. So again, we could see how the equilibrium plane has moved, in this case, simply because of the application of external applied load. Now, not to digress too much, but if we had a situation where there were global settlement after installation, we could have a situation where the equilibrium plane could now move downward again, right? As say the soil around the pile shaft settled, global settlement would now pull the equilibrium plane back down below the ground surface. So it's important to understand that this equilibrium plane is a very dynamic feature in any DFE application. It can move around whether the source of the drag load is residual load, global settlement, or in the more general case, both. Those of you who practice in the United States may have heard the term a driven pile is a tested pile. There's an industry organization, PDCA, devoted to pile driving. It's called the Pile Driving Contractors Association. They like to use the phrase a driven pile is a tested pile. Well, to that I will add that a driven pile is a pre-settled pile. And the reason is that residual loads, which our experience indicates are greatest for a driven pile, are to DFEs what pre-stressing is to Portland cement concrete. They both selectively preload and pre-stiffen the overall load displacement response to the system. Now in the case of DFEs, the benefit of residual loads is, as we know, for any DFE, it takes more displacement to mobilize toe resistance compared to shaft resistance. We may need only a few millimeters, a fraction of an inch to mobilize shaft resistance, but we may need tens of millimeters, several inches to mobilize toe resistance. So because residual loads mobilize some of the toe resistance, about 50% in this case history example, and I'll show you another example later on where it's almost 100% toe resistance was mobilized. This causes the post-installation externally applied loading to resisted primarily by the inherently stiffer shaft response, as negative shaft friction or unit drag load is reversed into positive shaft friction or unit resistance. Now, note that the current state of practice in the United States, Europe, and perhaps elsewhere uses DFE ground system stiffness as measured in a static load test as the primary metric for determining the geotechnical ULS of a DFE. So clearly residual loads are a benefit in this regard, but only if they are interpreted correctly. So I like this quote by Bucky Fuller that we should not fight forces, we should make use of them. And the point I'm getting at here is residual loads are an effective way to make use of forces. I do want to touch a bit on another interesting outcome from the NGI test program. Two of the four piles involved tapered piles. Now the pile we just looked at, what I'm showing you here is the residual load plotted as a function of depth. And the pile we just looked at was called pile DA in the Gregerson et al. 1973 paper. All right, so this is the distribution of residual load just plotted differently that we just looked at. And again, the equilibrium plane after installation was somewhere around here, a little bit more halfway down the shaft. Pile BC in the NGI test program, the upper 8 meters was constant diameter, but the lower 8 meters was tapered. The taper angle was very modest. It was only about 0.3 degrees of angle, which is approximately that of a very typical timber pile, at least here in the United States. And I suspect Norway at the time, which is perhaps one of the reasons why they happened to choose this taper angle. So the only difference between these two piles, they were both 16 meters long, is that pile BC, the lower portion was tapered. Now the interesting thing is, look how much larger the residual load is for pile BC compared to pile DA. As a result, the equilibrium plane for pile BC, the taper pile, is a little bit deeper. Maybe it's down around 10 meters, whereas here it was perhaps around 9 meters or so. So, to this observation that a driven pile is a tested pile and a driven pile is a pre-settled pile, we could add that taper makes it even better. And this is nothing new. The late Professor Ralph Peck noted this in a Highway Research Board publication back in the 1950s, that there is a very definite benefit to using tapered piles, at least in coarse grained soil. And I can attest to that. As I'll note at the end of this presentation, back in 2020, I published a monograph that's devoted entirely to the subject of tapered piles and their benefits. Well, we looked at the good news. Let's look at the not so good news. There can be some serious negative consequences of a geotechnical nature unless residual loads are correctly accounted for when you use various resistance verification tests in the field. Let's start off by looking at the traditional static load test that many consider to be the so-called gold standard for measuring the quote-unquote true geotechnical capacity of a deep foundation element. Now, typically in the United States, we use the so-called Davison offset method to apply to a static load test to determine the geotechnical ULS. I don't want to get bogged down in discussing the Davison method. I'm not a fan of it. There are others who are not a fan of it. It had a use, but not for static load tests. If you go back in the literature, you find that the late Professor Tom Davison developed this offset method for dynamic testing using the wave equation. It has long since been co-opted for static load tests. I think the reason people like it is that it is very easy to apply. In any event, this comes from another paper by Felinius. We're looking at the left-hand graph as a static load test curve as typically measured and presented. We're plotting the movement of the head of the deep foundation element, and there are interpretations of the toe and shaft movement, and here's the elastic shortening line. Now, using the offset method that's popular in the United States, we would interpret this curve to say that the failure load, quote unquote, is about 6,400 kilonewtons. And by the way, this 30 millimeter toe movement to define failure, this is a criterion, as I understand, that is popular in at least some Western European countries. So that's why Felinius is showing it here. Now, if we were to use a safety factor of 2 against this interpreted geotechnical failure load, we might conclude that the allowable load or maximum service load on this DFE was about 3,200 kilonewtons. Well, let's look at the true behavior, including residual load. First of all, the toe resistance here, Felinius is labeled as false, and it's false because it shows it's starting at 0 load, 0 movement. Well, in reality, due to residual loads, about 40% of the ultimate toe resistance was already mobilized at the end of driving. So in a sense, the true load displacement behavior of the toe is not beginning at the origin, but beginning at some point here. So the true toe resistance is greater than what we would deduce from this load test. Well, similarly, the shaft resistance shown here is false. It's too large, because to some extent we're double counting the shaft resistance. Right? Think back to what I showed you a few slides ago for the NGI test pile, where in the upper roughly 8 meters or so of the pile, when we went from end of driving to geotechnical failure, we had to move the shaft resistance from full negative, down drag, to neutral, to positive resistance, positive shaft friction or resistance. And that's why this is false. It's too high. The true shaft resistance is as shown here, and therefore this is the true load displacement relationship for the head of the DFE. Well, notice that applying the offset limit to this true curve, we would interpret a much lower geotechnical ultimate resistance. And therefore, our 3,200 kilonewtons, which we thought was safely a safety factor of 2, the actual safety factor is a little bit less than 1.5. So there's a 27% reduction in both the ultimate geotechnical resistance and safety margin based on the offset limit interpretation. It's a qualifier here. However, the true geotechnical capacity, where we don't use an artificial methodology like the offset limit or this 30 millimeter toe movement criterion, where we just look at what happens after we have tens of millimeters, several inches, in this case more than 3 inches of displacement of the head of the DFE. Notice that these two curves, both the as measured and the true behavior, including residual loads, what are they doing? They're approaching the exact same value of about 6,000 kilonewtons. So the true geotechnical capacity of this DFE is the same, as it must be. Right? This is a point that I made earlier in this presentation, that residual loads do not take away from the geotechnical resistance of a DFE. They don't take away from it. They don't take away anything. They may borrow it temporarily until you reverse the direction of movement. But if you push that DFE in the ground enough, there is only ever one true geotechnical resistance along a DFE. And this is when positive shaft friction or resistance has been mobilized along the entire shaft. There is no more residual load from whether it came from installation or from global settlement. There is no more drag load on the shaft. Again, it's a settlement issue. Notice that we have to move this DFE in the ground well over 3 inches in order to be able to measure the true geotechnical resistance. We have to get rid of all the drag load that was imparted, in this case, by installation as residual load. Well, there's even bigger problems with instrumented static load tests. This is a real problem, as we'll see, as neglecting residual loads results in interpretations of shaft resistance that are too large and toe resistances that are too small. Okay, to look at the problems that can occur with instrumented static load tests, when residual loads are not properly accounted for, I'm going to look at 2 monotube test piles that were installed about 30 years ago at Kennedy Airport, New York City. This was a test program that Dr. Felinius was involved in, apparently as a consultant. I was not working for the Port Authority by that point in time. If you're not familiar with monotube piles, these are basically steel pipe piles. They are made from cold form sections. They have a closed toe, and typically the upper part of the pile is a constant diameter and the lower part of the pile is a tapered section. And in this case, for these 2 piles, called pile 2, pile 3, the length of the tapered section was 25 feet, so a little bit less than 8 meters. These piles were intermediate taper, type J, which is an angle of about 0.6 degrees. So about twice the taper of a typical timber pile. Just to give you a frame of reference, the most common taper piles we use nowadays in the United States, alpha is about 0.95 degrees, so just about 1 degree of angle. Any event, this was an all sand site, and the way the piles are driven into the ground and then concreted after installation. So a very typical way of installing closed toe pipe piles in the United States, whether they are constant diameter or tapered, as in this case. The problem is that when you have such piles, it's common to install the instrumentation to measure strains and after driving and prior to filling the pipe with fluid concrete. So the empty pipe is driven in the ground, the instruments are installed, and then the pile interior is concreted. So the measured loads are based solely on measured strains within the concrete core during the static load test. And in this case, you see the measured loads for both piles very similar. The maximum load applied to pile 2 a little bit lower than pile 3. This pile had some construction issues. It was bent initially during driving, removed, had to be reinstalled. So actually the pile 3 is a little bit more accurate results. This, by the way, this is the pile that I showed in the opening slide, the results from pile number 3. But in any event, the measure load showed that these piles were carrying only friction, basically no toe load. And this sort of conclusion is not unique to these 2 piles. There are countless instrumented piles in the older literature where you see this behavior of little or no toe load, even in a coarse grained soil such as this site, all friction, if you will, or mostly friction. The problem is this interpretation neglected what turned out to be a rather significant residual load in each pile. And you see the estimated residual loads here. And the equilibrium plane in both cases is about the same, and it's quite far down the pile shaft. You see it's well beyond. You recall that for the Holman Island piles at NGI, it was about halfway down the shaft. Notice it's quite far down the shaft. In fact, it's about halfway down the tapered length. Well, the reason for that is that almost 100% of the tow load was mobilized for these two piles as residual load. Now, note that these monotube piles have a toe diameter of 8 inches, so about 200 millimeter diameter. So essentially, just about all of the toe resistance was fully mobilized as residual load, and that's why the equilibrium planes are so low. So everything from here down the equilibrium plane is drag load, just a little bit of shaft resistance plus rather significant toe resistance. And when you see the toe resistance of pile 3 is about 20% of the eventual ultimate load that was applied. So rather significant toe resistance, even though the toe diameter, as I said, is quite modest, about 8 inches or 200 millimeters. So the true load then in the pile, you see when we correct for residual load, is quite a bit different than the measured load. And this is the point I'm trying to make, is that when you have a pile such as this, where it is installed in stages, you drive the closed-end steel pipe, you install instruments, then you concrete the interior of the pile. The difference between measure load and true load can be very, very significant, and obviously it's going to affect how you interpret the load-bearing characteristics. And Fellinius noted this point with this quote here, which I take from his most recent edition of what he calls the Red Book, which he came out with earlier this year. Basically saying that if you have a instrumented static load test and don't correct for residual loads, you've wasted your time and you've wasted your client's money in the process, because everything you will interpret is basically going to be wrong rather significantly in some cases. The reason I'm spending time and emphasizing this is, if you think about it, there are countless resistance forecasting methods for deep foundation elements that are and have been in everyday use for many, many decades, going back to the 1950s in design practice, that were either developed or at least calibrated using distributions of shaft and toe resistance that were inferred from instrumented static load tests that were not corrected for residual loads. It's important to understand that these methods, these forecasting methods, tend to overpredict shaft resistance, underpredict toe resistance, but these two wrongs do not make a right. Right? I've heard people say, well, yeah, I know the toe resistance is wrong and the shaft resistance is correct, but when I add them together, I get the right answer. No, you don't. If you get the right answer, it's just as pure dumb luck. It's just happenstance. It's not two mistakes canceling each other out. So this is quite serious. You think about all the countless analytical methods that we use in everyday design practice. Whether it's what we call an indirect method that is based on soil mechanics principles, or it's a direct method that's based on some correlation with, I don't know, SPTN values perhaps, like Nordland did back in the 60s, or perhaps it's against cone penetrometer values. All of these correlations tend to be rather significantly incorrect. Now, these same issues of a mismatch between shaft and toe resistance can exist with newer resistance measurement methodologies that are based on dynamic measurements. And this comes from yet another Fellinius paper, where he had a pile that was subjected to dynamic measurements and then interpreted using the CAPWAP methodology to give this distribution of shaft and toe resistance after driving. But as Fellinius pointed out, the CAPWAP interpretation did not account for the forces that were already locked in as residual loads. And in this case, the toe resistance is what? It's about maybe 20% roughly of the ultimate toe resistance. And again, an equilibrium plane that is rather far down the shaft of the pile. So we see then when correcting for the for the residual load, the true load distribution is rather significantly different from the CAPWAP interpretation. Well, I now want to move on to discuss issues related to the effect of residual loads on the structural behavior of a DFE. Unfortunately, with structural aspects, it tends to be all bad news. We saw with geotechnical aspects, there was good news and bad news. You got to make use of the good news and correct for the bad news. But with structural behavior, it tends to be all bad news. That's because there are some very serious negative consequences if residual loads, which produce compressive normal stresses within a DFE shaft, are not properly accounted for. And again, I will illustrate this with case histories. This is because, unlike with geotechnical behavior, where we can take drag load and from residual loads and can reverse it into resistance simply by causing the DFE to settle, the compressive material stresses within a DFE shaft that result from post-installation applied loads are additive to and cumulative to those of the residual loads from DFE installation. So again, with the geotechnical aspects, we can, if we settle the DFE enough, we can cancel out the drag load and convert it to resistance. But unfortunately, we can't do that with the structural aspects. And that's because all the loads involved are compressive in nature. They're compressive loads, compressive stresses, and they simply will build up on each other. Another thing is that, unlike with geotechnical behavior, where residual loads tend to impact only the DFE behavior under axial loading, with the structural behavior effects from residual loads can affect the behavior of the DFE under horizontal and/or moment loading as well. And this is something I don't see talked about. And that's because the compressive normal stresses from residual loads are added to and cumulative with the normal stresses, both positive and negative, created by the flexure in a DFE shaft that results from horizontal and/or moment loading. And I'll illustrate that qualitatively in a minute to show you what I'm talking about. Well, again, to look at some of the structural aspects, let's go back to our NGI test program. This is the same 8-meter long constant diameter pile that we looked at initially. In this case, I've added another graphic that shows the axial compressive force in the pile as a function of depth. And I want to focus on the half Q90 load. Again, this is half of the geotechnical ULS, so nominally the allowable load or maximum service load in the pile. And here's the equilibrium plane for that condition. And the point I want to make here is that in this case, at 230 kilonewtons, roughly 50 kips applied to the head of the pile. Now, typically, when we design a pile structurally, we'll often think that, well, the largest load in that pile, or the DFE in general, is going to be at the head. Well, not necessarily, not when residual loads are involved. And in this case, we see actually the largest axial force in the pile is at the equilibrium plane, where it's 275 kilonewtons, or about 60 kips. So the point I'm getting at here is that the maximum force in the pile, which of course has to be at the equilibrium plane, is about 20% larger than the load at the head of the pile. And this difference is something that is typically not considered in the structural analysis and design of a DFE. Using that same pile from Norway, I just want to illustrate, if we have deep foundation elements subjected to moment or horizontal loading at the head, we know that the maximum moment in the shaft will typically be at some depth below the ground surface. All right, so the peak is peak moment, and therefore the peak stresses caused by that moment are going to be somewhat below the ground surface. The point I'm getting at here is you have to be concerned about this peak occurring somewhere near this peak. And again, at least on the compressive side, these compressive stresses will be added to the compressive stresses due to the moment and shear loading at the head of the DFE. This is not something I see talked about at all in the literature. Let's look at an even bigger problem that can occur when you have piles such as the monotube piles I talked about at Kennedy Airport in the 1994 test pile program, that you have a DFE that is installed in parts, if you will. Now here I'm just going to focus on pile number 3. So what you see in this graphic is as a function of depth, and I've non-dimensionalized the depth by simply dividing the actual depth by the total length of the pile. And this is the transition between constant diameter and tapered sections. And what I'm showing you here is the residual load that was estimated after installation divided by the maximum applied load at that level at the end of the test, expressed as a percent. And we see that, again, almost 100% of the ultimate load was already mobilized as a residual load down at the toe. And we see that within the tapered section, the residual loads are a fairly substantial part of the eventual ultimate load in the pile shaft, less so in this upper portion of the constant diameter section. So this is a point I made earlier, that in this pile, or these two piles, almost 100% of the ultimate toe resistance was already mobilized as residual load. Now these graphics look a little busy, so let me explain them a bit. Okay, what I'm showing you here is the applied load on pile number 3, again as a function of normalized depth. And here we see the transition from the constant diameter section to the tapered section. And over here I'm showing you the stress in the steel pipe and the stress in the concrete core. And here's SI units up here, imperial units down here. And the same thing here, SI units here, imperial units down here. So here's the residual. Let's look at the residual loads first. We've seen this previously. Here's the residual load distribution, equilibrium plane, quite far down the shaft, well within the tapered section. And here we see the stresses in the steel pipe due to the residual loads. And notice that the stresses do not peak at the equilibrium plane, rather they peak at the toe of the pile in this case. And this illustrates quantitatively a point that I made earlier, and that is, although the force, the axial force from residual loads always peaks at the equilibrium plane, you have to be careful. The axial compressive stresses, normal stresses, may or may not peak at the equilibrium plane. And in this case, they don't. Why? Even though the force due to residual loads decreases below the equilibrium plane, so does the cross-sectional area of the pile because we are within the tapered section. So the pile diameter decreases, the cross-sectional area of steel decreases, so we have to do an independent stress calculation. And in this case, the peak stresses actually occur at the toe of the pile. Now let's look at the theoretical shared load. And this would be based on the traditional stress-free Wishton place model. Okay, we know that if, as in this case, we have a pile where we drive the steel pipe, then we fill the interior of the pile shaft with fluid concrete, the concrete hardens, and then we sit down and do a structural analysis to figure out, okay, what's the stress in the steel shell, what's the stress in the concrete core. And every time I've ever done this calculation in the past, and just about everybody I've ever seen do this calculation, always assume that both the concrete and the steel start from a zero stress position starting point. Okay? So assumes that the stresses in the steel pipe and the concrete core are zero initially. They both strain the same amount, and then it's a straightforward calculation to figure out how the stresses are apportioned between the two materials. And this would be the distribution you'd get of applied load. The solid blue curve would be the stresses in the steel. The solid brown or dark red curve would be the stresses in the concrete. But these are wrong. They're wrong because we have not considered the residual stresses that exist in the steel shell before we concrete the pile. All right, so in reality, the shared load is less than we think because that steel pipe is already stressed by the residual load before any concrete is even put in there, no less hardens, to be able to support any load. So now when we apply the 2,500 kilonewton load at the head of the pile in the load test, the dash blue curve shows the stresses in the steel because the stresses in the steel build on the stresses that are already there. So the actual stresses in the steel are the sum of the green curve from residual loads, the blue curve from load sharing with the concrete core. The steel stresses are much higher than we imagined. Conversely, the stresses in the concrete core are a lot smaller than we think, right? Because the concrete has to carry only a smaller portion of the load. So the dash curve here shows the actual stresses in the concrete versus what we think is there. And we see the differences are quite significant, especially down here in the lower portion of the tapered section of the pile. And in fact, we see that in the lower portion of the steel shell is actually overstressed by about 100% in places. What I mean is the stresses in the steel pipe are about twice what we think are there based on the traditional assumption of starting from a zero stress in both the steel and the concrete. When I first started looking into this some years ago, I was shocked. I mean, believe me, I spent more than 50 years of my professional career working extensively in the New York City metropolitan area where concrete-filled pipe piles, either constant diameter or tapered, are the foundation of choice in many, many, many projects, both in the past and continuing to the present. And it was quite a shock when I realized some years ago that things that I've been doing in the past, just about everybody I know around me was doing in the past, are something wrong. meaning that there are who knows how many, countless number of piles are, the steel is overstressed and the concrete core is understressed. I think the only reason we have not had problems is that historically the New York City building code was very conservative with the allowable stresses in both the steel and concrete of a pile. Had very high safety factors on both the steel and concrete portions, much higher safety factors than you would see applied to steel or concrete in, say, the superstructure of a building. So I think it's just by dumb luck of a very conservative building code, we have not had a lot more problems from this stress issue. Well, that concludes the main portion of what I wanted to talk about. There's just one additional issue I want to mention before I close out this presentation. And that is separate from but related to the material normal stresses within a DFE shaft that are due to residual loads from installation, or the manufacturing residual stresses in the steel sections that are key structural components of many DFEs. For example, steel pipe, which nowadays is usually spiral welded as opposed to seamless pipe that was predominant in the past, as well as HP sections, H-pile sections, have residual stresses from their manufacture. I'll just digress and say that when I started out my professional career in the New York City area in the early 1970s, many organizations did not allow spiral welded pipe for deep foundation elements. They insisted on seamless pipe, and that's because spiral welded pipe had a bad reputation at the time of the welds not standing up to pile driving stresses. And we can see that by the way that spiral welded pipe is made, right? You start out with normal coil steel, it's sent through rollers, it is twisted into a circular shape, and then the butt joints between these twisted sections of steel are welded together. And this is the final result you get. All right, this is a slide for some tapered tube piles installed at Kennedy Airport, and you can see here the weld line on the spiral welded pipe. Now, modern spiral welded pipe, when done correctly, is quite robust. And I always like this slide. This happened to be another slide that was taken at Kennedy Airport in the 21st, not that long ago, it was earlier in the 21st century. This was a tapered tube pile that the head of the pile was not properly lined up with the ram of the pile hammer during installation. And as you could see, because of the driving eccentricity, the steel, the upper few inches of the pile yielded. Now keep in mind, this is 50 KSI yield steel, so this is, you know, stronger than average steel. So you could see really this classic kind of accordion yielding of the upper few inches of pile as the steel stresses were greater than yield. What to me is enlightening here is notice that the welds did not separate. So this is a classic case of a good weld, if you will, where the strength of the weld is stronger than the parent material on either side. So although the steel yielded, the welds did not separate. And I emphasize that because, as I said, that was the bad rap that spiral welded pipe had many decades ago, that the welds were not as high quality and that you could drive a pile and just have this thing unspiral before your eyes. Quite a bit different now, which as a result, we tend to see spiral welded pipe used because it is presumably cheaper or less expensive than seamless pipe. And as I noted, I used this graphic earlier, we have mill stresses, rolling stresses in hot rolled sections as well as cold form sections. And this just shows in a typical wide flange section, as we would imagine for an H-pile, that there are stresses as well. Now, the point I'm getting at here is that the presence of these residual stresses has historically been ignored in the design state of practice as well as academic research for DFEs, and remains so in the present. In fact, I've looked, and the subject is not even mentioned in the published literature, no less discussed. So I'm mentioning it here because obviously these manufacturing-related stresses, whether from rolling or cold forming or welding, they are, in principle at least, or theory at least, they are additive to the material normal stresses from residual loads from installation, as well as the externally applied loads, both axial and horizontal moment. So just something to think about. Maybe we should also think about these manufacturing stresses when we're thinking about residual loads as well. So to summarize and conclude this presentation, residual loads from DFE installation impact both the geotechnical and structural behaviors of a DFE in multiple ways, such that residual loads should always be considered in both routine design practice as well as academic research, especially when the results of academia are used to produce analysis and design methods in design practice, which is typically the case. And this goes back to what I said earlier, that I think a lot of the analytical methods we use in design practice, the shaft estimates are too small or too large, and the toe resistant estimates are too small. So I think what is very much needed at this point in time is for all stakeholders in the deep foundation industry to at long last recognize the existence and mission critical importance of residual loads for all types of DFEs in both design practice and academic research, and above all, to deal with these residual loads correctly. Really what we need is an industry-wide investment to further investigate residual loads for all types of DFEs, including and especially perhaps some of these newer types that are drilled or torqued into the ground that are gaining market share. And from this, develop some user-friendly methodologies so that we can forecast residual loads during the pre-construction design process, so that these loads can be considered in routine design practice. That's really what we need right now. As I said, there were some early efforts back in the 1980s along these lines. I think with the technology we have nowadays, we could do a lot better to bring some of these methods to either improve them or to come up with completely new methods to make them user-friendly for the typical design professional in everyday practice. I have to remember, as I hopefully have conclusively shown everyone who takes the time to sit through this presentation, residual loads exist. They don't disappear when we apply external loads, and they can be very significant to the geotechnical and structural performance of a DFE. So these are facts, and they're not going to cease to exist if we continue to ignore them. So I think we're much better off as a profession if we simply come to grips and deal with them properly. With that, I will just mention this monograph that I wrote back in 2020 on tapered piles. It gets into a lot of these issues of residual loads in much greater detail. For example, I have a whole appendix where I just talk about the NGI test program at Holman Island, talk about all 4 of the piles that were installed there. So I recommend that to you if you want some additional information on the subject. You can buy this. This is print on demand. It's a softcover book. You could order from any online bookseller anywhere in the world using this ISBN 13 number. And with that, I want to say thank you for your time in viewing this presentation. Hopefully you've learned some new things, and will be added to the roster of those who are firm believers about the importance of residual loads with all types of deep foundation elements.